Thank you for coming back to me. The room is approximately as full as yesterday. This means a lot to me. I haven't lost you all or outraged you. This is good. Today we continue our journey into quantum complexity, which was the job description that Alex gave me when he hired me for this venue. And I already alluded to it yesterday that there are several ways of interpreting complexity in the quantum case. And arguably the most natural and maybe most interesting case would be to talk about basic quantum complexity classes, like what is the analog of P, what is the analog of NP. But I already confessed yesterday that I purposefully misunderstood that and will talk about a different notion of complexity today, because Alex is much, much better suited to give a kind of like quantum complexity theory class than me. And instead, I kind of like want to talk about complexity in the sense of a cost associated to execute a certain computation, a fundamental cost. Kind of like also when it comes to incompressibility of computations and fundamental lower bounds. And there's like some basic results from classical computer science that I want to kind of like remind you of. And in the last two lectures, we will kind of like try to make sense of them and generalize them to the quantum setting. And this is not as straightforward as you might think, because if you paid attention yesterday, the quantum circuit model, as I wrote down already here in the recapitulation, is very much an alternative circuit model of computation. So it's kind of like, on a high level, it looks very similar to the logical circuits you learn in hardware design. But if you look a bit closer, I've kind of like sketched part of the circuit here. There's also notable differences. Like one thing that I didn't write here because it will not be so important for today is that we have a designated read-in and read-out stage in the QPU. And the readout stage in particular is interesting and destructive. I tried to convey yesterday with this Bourne's rule that if you do a readout, the outcome is always probabilistic, and it's like an importance sampler. And the importance sampling distribution depends on the logical content of the quantum state vector psi just prior to the readout stage. So there's some randomness involved, but also, and potentially more scary for counting and complexity arguments, is the Solovay-Kitaev theorem that I mentioned yesterday, which tells you that with very few elementary quantum gates, Hadamard, T-gate, and C-naught, you can actually approximate continuous unitary transformation up to arbitrary precision. Okay? And this means that if you want to thoroughly analyze this question, discrete math is not enough. Kind of like one reason why I really like the circuit model of computation, and I teach it in my basic computational complexity classes, is with circuits you can always count with logical circuits. And you can say a lot with counting. But in the quantum case, counting is scarier and more difficult because we have continuous degrees of freedom. Okay? And in the lecture today, I want to kind of like show you a general proof technique, which I like very much. I think it's very powerful. I learned it from the likes of Roman Vershinin, which is a connection to what Heiko did, where you can use the probabilistic method and randomized constructions to also count on continuous objects. Okay, so today, this lecture is a tutorial on how to use the probabilistic method to expand counting arguments that you think should be valid for quantum circuits rigorously to the quantum setting. Okay, so this is what we do today. I have the privilege of teaching you another lecture today in the afternoon. And what we will do today in the afternoon is we will take the probabilistic counting arguments we did now and we will partially de-randomize it. A bit similar to the notion of T-wise independence. And then we'll get kind of like a cool result that will tell us that random circuits, when we start building up random quantum circuits, by just choosing gates randomly and make them longer and longer, are with very high probability incompressible. Okay, so that means that the complexity of a random computation, also in the quantum sense, must grow linearly with the size or depth of the circuit. This is something that you would intuitively expect, because randomness doesn't have any structure, and so we would expect that maybe the Kolmogorov complexity of a random circuit would grow. This will be kind of like the final result in the afternoon where we'll prove this. Okay? But today we look kind of like at the base case and ask ourselves how expensive, how complex is a generic or typical quantum circuit. Okay, so today we ask the typicality question, and in the afternoon we will de-randomize it. Okay, so that's kind of like what awaits you. And before starting, I remind you, my blackboard writing is horrible, even with this famous Japanese chalk, and time to prepare. Here is the link to Alex's GitHub page where you can find the lecture notes that also cover today's lecture and in the afternoon. And more generally, if you like, kind of like the way I present things, I put a lot of dedication into lecture notes, and you find several of them on my webpage about quantum computing, about complexity theory, about multilinear algebra. It's very easy to find if you want to know more. Yes?
The link is slightly wrong.
Oh. Thank you. This is bad. Thanks, Alex. Right? Thank you. But maybe you have it still from yesterday, so I encourage you to fire it up. Today will be much slower than yesterday, but conceptually, hopefully, a bit more interesting and new. And we will also deal about continuous probability distribution, so this is maybe kind of like not something that you are, as computer scientists, so familiar with. So again, please interrupt me at any point if you have clarifying questions. This gives me the chance to take everybody with me. Okay, so just a very quick recapitulation from yesterday. QPUs are alternative circuit models of computation. This is what we showed yesterday, and you can also see it here. And it's kind of interesting because the circuits themselves are reversible, which is interesting if you want to use counting arguments for complexity. Because what reversible circuits means is that it is not so unlikely that two randomly selected gates, can meet each other and cancel out. So kind of like in normal circuit counting, we are aware that different circuits can lead to the same functionality. This effect is possibly more pronounced in reversible architectures because gates can really annihilate each other. Okay, so it's kind of like reversible and continuous. Okay, kind of like there's kind of continuous degrees of freedom, at least in the limit when we take more and more gates. Okay, and just to remind you, kind of like a CPU can always be polynomially at a polynomial overhead. I'm being a bit sloppy here, simulated by a QPU. And what you do is kind of like you take the circuit you are interested in, the circuit computation, you make it reversible, which you can do with a linear overhead, and then you run the reversible implementation on your QPU. And conversely, a QPU can always be simulated with an exponential overhead on a CPU. Okay, so kind of like the two, in the grand scheme of computability, the two are equivalent. But there's possibly an exponential difference in between. And something I forgot to mention yesterday, but I want to state it today, is that this has kind of like an interesting nuance for the Church-Turing thesis. Maybe you remember that the Church-Turing thesis, it's not a theorem, it's a belief system that we in computer science have, where we believe that every process in nature or engineering can be simulated on a Turing machine. This is why we teach Turing machines in basic computational complexity. And up to quantum computers, the strong Church-Turing thesis was prevalent, where same statement, but with the additional quantifier that a Turing machine is capable of simulating any computation on another device or any process in nature with only a polynomial overhead. Okay? So the quantum computer, what you see here, yes?
What do you mean by polynomial overhead if it's a natural process?
Good question. Let's talk about this over wine in the evening. I think the Church-Turing thesis is not a rigorous statement. It's a belief system. And quantum computers don't change the fundamental nature of the Church-Turing thesis. We can still simulate quantum computers on classical computers with exponential overhead, and here it's precise. But it might violate the strong Church-Turing thesis because we don't know how to get rid of this exponential overhead. And so there's really windows of opportunity potentially where we can save exponential runtime by using QPUs. But we don't have that many solid examples. The most solid one I know is integer factorization, But as you may know, integer factorization is not believed to be a really hard problem. Okay, so this is a recapitulation from last lecture to kind of like remind you about the stakes. And today, I kind of like want to take a very basic result now about classical circuits, which I like very much. This goes back to Shannon, and try to make it work in this quantum setting. Okay, and I think there's a famous theorem by Shannon, which says almost all n-bit Boolean functions, so this is a function from n bits to a single bit, require exponentially large circuit representations. Okay? Or almost all Boolean functions are exponentially difficult to compute or lead to CNFs that are exponentially large. Short comment. We work in a circuit picture. What does large mean? For me, there are two natural kind of like complexity measures for circuits. One of them is the circuit size, which is the number of elementary gates. And the other one is depth, which is the longest path between an input node and an output node in the graph representing the circuit. Or in other case, optimal parallelized runtime. Kind of like this number of layers you need if you can do things parallel. Longest path. So roughly speaking, circuit size is the circuit analog of the runtime of a Turing machine. And circuit depth is parallelized runtime, where you allow yourself to do computations in parallel. In quantum computing, because circuits are reversible, these two things are kind of related. And when you want to parallelize, you can only ever gain a speed up or an improvement that is linear in the number of qubits here. Okay? So for today's purposes, I will think about very long circuits, which are much, much larger than the number of qubits. And then these two become comparable. And when in doubt, I will use circuit size, because it's easier to count. Okay? The same is true here. Kind of like with exponentially large circuits, you can use circuit size. And I'm sure many of you know this theorem. I think it goes back to Shannon. Would anyone be willing to tell me how to prove that? It's a beautiful counting argument. Not so difficult. And it's not a trick question. I'm not trying to fool you. I just try to engage you. Yes. Yes. Why? Yes, true. Yes. Great.
The number of circuits that say S.
Yes. I'm now being a bit sloppy, but I think there are at most probably n to the S circuits of size S. Right? I guess. Something like this. Sloppy. Hey, thanks. Well done. And now you start comparing the numbers, right? And if you want to cover, and this is an upper bound because two circuits can lead to the same functionality, but you have to reach this number, and this is doubly exponential. And so the only way to achieve that is to let your circuit size also become exponentially large. Right? And one thing I want to point out, which is very nice about this counting argument, is it also gives us a notion of typicality and how we interpret almost all. Because what this also means is that if I were to sample one of these 2 to the n functions uniformly at random, then with overwhelming probability it would not admit a short circuit representation, just by counting. Because just this set is just much, much smaller than this set. And when I pick uniformly from the set of all Boolean functions, I can use Laplace's definition of a probability, the number of good events over the total number of events, to really prove that the probability of a uniformly sampled Boolean function to be expressive in sub-exponential circuit size is doubly exponentially small, basically. Okay? So I think this is a very nice result, and also kind of like you can either use counting, or what I really like is also like this uniform sampling, and then arguing that with overwhelming probability the circuit you got, or the full function you got, does not admit a short circuit representation. Okay? The goal for today is to show exactly the same thing for quantum circuits. And thanks again, super great proof. With what we know, this is not so easy. Kind of like one thing that I can generalize is this. Yesterday I presented you with an elementary gate set of quantum circuits. We now have kind of like circuit size as a measure. We can start counting the number of different reverse circuits we can build with S gates. Because this is still a circuit. There's no, it's just a graphical representation. This part is much, much harder. Kind of like, it's an example of why discrete math is good. We can count Boolean functions. Can we count the total number of unitary 2 to the n by 2 to the n matrices in a meaningful sense? The answer is probably yes, but it's not so easy. There's continuous degrees of freedom. And the proof strategy I want to present to you today is one way of using randomness and concentration in order to make sense and arrive at a very similar statement. So what we will prove today in this lecture is a new theorem or kind of like what you can prove with the methods I'm going to show you is almost all unitary u to the in C 2 to the n times 2 to the n require exponentially large quantum circuits to approximate. Okay, this would be a generalization of the above results to quantum circuits that is natural to me, because yesterday we saw that every unitary matrix, 2 to the n by 2 to the n matrix, is a valid quantum circuit. And so this should be our generalization of the Boolean functions. And what I want to prove today is that all unitaries, if we take one of them, sample one of them at random, then with overwhelming probability we cannot approximate it with a small or polynomial size quantum circuit, even if we choose very poor approximation. Kind of like really large errors, it's still kind of like hopeless. Okay? Yes?
Just to confirm, so the first counting argument also gives you that most Boolean functions cannot be implemented by small quantum.
Yes, yes, true. True, very good point. So this is the gist I want to prove today. And to keep it a bit simpler, I will actually do a variant of this question, which doesn't make sense in the classical case, but it makes sense in the quantum case. So this is kind of like the theorem that you could prove now. What we will actually prove is almost the same except I will prove it for state vectors. Okay, so the concept I have now is, like yesterday, I told you how does a QPU work. We have like a simple initialization stage where we load in bits into our quantum computer, and then we start applying a circuit. And this will produce a final state vector. Okay? And now we can also ask ourselves, how expensive is this final state vector to generate in principle? By fixing a simple initial state configuration, like every bit is set to 0, and asking ourselves what is the shortest possible circuit that gets us from the fixed initial state to an approximation of this state vector. Okay? And I hope that you can intuitively see that this is related to the complexity of a unitary transformation, because here we kind of like ask ourselves about one concrete computational path of a quantum circuit and bound this exponentially from below. And this probably suggests that the circuit in question is difficult to begin with, unless we put like a lot of computational power into generating these initial states. Okay? I do that because it makes the math a lot simpler, but the techniques I'm going to tell you also allow you to handle the unitary case. And just as a side note, this question is boring in the classical case. In classical case, the classical analog of a quantum state is a bit string. And if I have an n bit string, the largest complexity of an n bit string is n if I start with all zeros, because I must flip at most n bits to get the 1, right? But in quantum it's different. There we will see that even kind of like the quantum state vectors, the logical content for one input are typically exponentially expensive to generate. Every n bit string can be generated with at most n negations. Yes?
Why Johnson the straws not sufficient to count these state vectors?
What do you mean?
Like, you know that there are doubly exponentially
Yes.
almost orthogonal vectors?
Yes.
So why isn't it sufficient to...
Yeah, we will do that. I just want to make this is like the gist. I just want to make this rigorous and show how this works.
Okay, perfect, okay.
Thanks for spoiling. So Alex had a great intuition. Maybe we can use still some type of counting arguments or dimensionality reduction, or like some arguments that allow us to approximately count the number of state vectors. And then this result is not so surprising, because remember that a state vector has dimension 2 to the n. So this is in dimension 2 to the n. And so it's a huge, very high dimensional vector. And we expect that there's very many of these high dimensional vectors, at least, let's say, linearly many or polynomially many in this dimension. And this will then allow us to kind of like make a similar argument. The last thing I need, and I'm writing it down here, is a useful distance measure. Kind of like I mentioned, approximate here, because we now have continuous degrees of freedom, and it's not just counting. Because when we say kind of like two state vectors can be very, very close to each other, and then we shouldn't call them different state vectors. So we need some figure of merit of closeness to make sure what approximate mean. Okay, and so kind of like our measure of closeness is the fidelity. And the fidelity of two quantum state vectors, I call them psi and phi, is just the inner product between the state vector squared, and this is kind of like the angle. Okay, and this is a number from 0 to 1, and it's 1 if the two state vectors are parallel or anti-parallel. but kind of like this anti-parallelity doesn't matter in quantum. It's just the angles. And it's 0 if the two state vectors are completely orthogonal. Okay, so this is a very kind of like nice distance measure. And nota bene, 1 minus the fidelity is now really a metric. Kind of like this is 1 if the two are the same. 1 minus this guy is 0 when the two are the same. And this is actually in 1-to-1 correspondence, I think with the square root, to the total variational distance. I'm now simplifying a bit, but kind of like the generalization of the total variational distance between the two state vectors. And as we learned from Amir yesterday, this actually has an operational interpretation. So if the fidelity is very close to 1, 1 minus the fidelity is very close to 0, and that tells you something about all possible events or tests or questions you could ask about the two distributions, that they are never too far away from each other. Okay, now this is kind of like very quick. What we will need today is, this is just an inner product squared, so it's an easy object to work with. But geometrically, it carries a lot of nice meaning in the quantum sense, including these nice operational interpretations of these F divergences that Amir mentioned yesterday. And it's kind of like the generalization of the TV distance. Okay? So let's prove this. And the proof proceeds in 3 steps. Kind of like proof part 1. When in doubt, choose a random state vector and see how it behaves. This is kind of like the main gist of today. Proof part 1, choose a random state vector. And what do I mean by random? A random state vector sampled from all possible states, and compute expected distance to a fixed and arbitrary other state V, which is also there. Okay, I want to use kind of like random arguments to get an intuition. And the first starting point is I fix any reference state vector. This doesn't have to be a simple one. I just take any one of them. It's like one direction, kind of like one of these huge vectors. And then I sample another one uniformly from all possible state vector possibilities. And then I can ask myself, how close are they? Right? And here's a nice lemma. This tells you that in expectation, when I take the right measure, if I sample this random vector in the right measure, I take the fidelity, which is the inner product of these vectors squared. This is my distance measure. It's 1 over the dimension of my vector space. And remember that the dimension of the state vectors is exponential in the number of qubits. So when we have many qubits, the dimension is huge, and this is very small. What this geometrically means is that if I randomly sample a state vector uniformly from the possibility of all state vectors, then it is almost orthogonal to every fixed reference. Okay? And this, maybe you can see already, could be used as a starting point for a counting argument, because if kind of like the expected behavior of a random state vector is to be almost orthogonal to one fixed vector, it's probably going to be almost orthogonal to many fixed state vectors as well. And then we can use this, the fact that this is arbitrary, to kind of like start generating these reference state vectors with circuits. Okay, it was a bit quick, but this is the main gist. What we now need is kind of like a nice uniform measure on state vectors. And geometrically, I remind you that every state vector is a complex valued unit vector. So they all live in a very high dimensional complex unit sphere. If I asked you to draw uniformly from a sphere, you have kind of like an intuitive meaning what that means, right? What this should entail. Like think about the globe, then every location on Earth should be sampled with the same probability. This would be a uniform measure, right? And one way to characterize that is if you choose this measure, which treats every square inch of planet Earth or a sphere fairly and equally, then this has to be invariant under orthogonal or unitary rotations, because the sphere is round and it remains the same if I rotate it. Okay, and this is also one way of characterizing this. So kind of like here, we sample uniformly from the sphere, and this means that this is the unique, unitarily invariant measure. And this is sometimes called the Haar measure, if you know group theory. It's very easy to visualize. It's very difficult to code, actually. But conceptually, I think it's a beautiful result, and an important property is this rotational invariance, this unitary invariance of the measure. Okay? And I tell you that if we fix an arbitrary reference state vector or vector in a high-dimensional sphere, and then we sample uniformly from the sphere, in expectation, you're almost orthogonal. Okay? How would you show this? There's at least 3 ideas. If we have kind of like this nice uniform measure on the sphere, does it really matter what the actual reference vector is? No, right? I can rotate. So I can rotate the reference vector to a very simple vector, like for example, the upwards direction. Like a vector that only has one coordinate with 1 and zeros everywhere else. Right? Then one thing you could do, if you kind of hate yourself and want to work hard, you look on Wikipedia and find generalized spherical coordinates. They kind of like give you the volume form of high-dimensional spheres. You did rotational invariance, so you only have to compute one coordinate. You plug it in, you integrate. This works if you use this trick, but it's not something I like to do. I don't know about you. There's 2 alternative, more general ways of doing that. I'm heavily biased, and I will explain one. And I will quickly also tell you about the other. The second idea, kind of like proof, kind of like unitary invariance, allows you to rotate V to, let's say, the first vector, which has a 1 and 0 everywhere else, without loss. And then strategy 1 is spherical coordinates. And then do it by hand or use Mathematica. The second idea is I find it much more elegant, and it's kind of like a powerful idea. It's called Gaussian integration. Who of you has heard about Gaussian integration? Great. Some have. I mentioned before that we have a uniform measure on the sphere, and kind of like the expectation value here is like an integral over a very high dimensional sphere, right? And yes? Yes, this is what we will do. This is the solution, the third solution, which I'm heavily biased towards. But before quickly Gaussian integration, it's a beautiful idea. What happens if I replace the random vector h, which is on the sphere, and so it's normalized, which makes it difficult, by a Gaussian vector with a standard complex valued Gaussian vector. I have to do complex values because my sphere is, yes? Yes. 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 Yeah, but you have the absolute value, which gives you this small bias of 1 over d. You don't get 0. Yes. I think you're right. Very good. I fully agree. We will later do higher moments, and then I guess the symmetry arguments will become a bit more complicated. But for now, you're absolutely right. Thank you. The idea in Gaussian integration is you kind of like, you don't like spherical coordinates, and so you just solve a different problem. What if I instead computed the expectation value of this function with a standard Gaussian vector, where each component is an independent Gaussian random variable? Okay? For me, this is an easier task, because in particular with this rotation, we only have the first coordinate, and so the question of computing the Gaussian expectation here really just boils down to computing the expectation value over two Gaussian random variables of g plus ih squared, which is the same as eg g squared plus eg h squared, which is just 2 if I have a standard Gaussian random variable. Okay? So kind of like in Gaussian random vectors, the coordinates are all independent. And so I can use Gaussian integration and kind of like the way of computing Gaussian expectation values to compute these functions. And this is not such a bad idea, because one of the defining properties of a Gaussian random vector is that its distribution is also orthogonally invariant, right? So in a way, if you choose a random Gaussian vector, the direction is a uniform random direction on the sphere, and what you're left with is this annoying radius, the length, which is not quite 1, but it's kind of like square root of the dimension. But there's a beautiful fact from the study of Gaussian random vectors that tells you that if you move into spherical coordinates, a Gaussian random vector decomposes into a random variable that tells you the radius and another random vector that tells you the direction. And the two are statistically independent. So you can actually take this Gaussian integration formula, compute the thing you want very easily, and then rewrite it in spherical coordinates as a product of a radial contribution and a direction. And this will factorize, and then you have the expected integral over the direction here. And the radius gives you some dimension dependence. If you do it in this case, you will exactly get this 1 over d, because the dimension comes from the expected squared length of a Gaussian random vector. I know I was very, very quick, but this is a powerful idea of computing averages in these high-dimensional spheres. Is this kind of like the one you know, the trick? And the big advantage of this that I used in the past is you can really use this for non-analytic functions as well. Kind of like Gaussian integration with these tricks allows you to kind of like also really kind of like compute expectation values of very difficult functions where you don't even have a Taylor expansion, so you couldn't approximate it with the moments. Okay? Just as a side trajectory. If you have to integrate over high-dimensional spheres, just do Gaussian integration. What I want to do is a technique that is maybe a bit more difficult to get going, but it's more general and convenient for these types of problems once you've understood it. And it's kind of a symmetry argument. If I take the thing I care about, this V inner product with H squared with the expectation value, I can rewrite this as V inner product with H and the adjunct H inner product with V. Okay? And now I can view this as a quadratic form evaluated at an outer product. I can pull in kind of like this. This is the same as V star. This is like from the left, expectation over H, H dagger, H adjunct, V star. Sorry, V. Kind of like this is a matrix, an average over rank 1 matrices. This is a row vector and this is a column vector. And to the gentleman in the very back, this would be easier in the bracket formalism. I now on purpose don't use it to not confuse. Okay? And so I've seemingly made the problem more complicated by kind of like computing here an average over rank 1 matrices. Okay? Let me call this guy A. Okay? And now, what is A? A is really the integral over all vectors on the sphere of h star dh. I uniformly integrate over the entire sphere. Right? This is a very high rank matrix. Let me rewrite this as an integral over all possible unitary rotations of u applied to one designated fixed point on the sphere with u dagger du. Rather than integrating over all vectors on a unit sphere, I can start with a fixed vector, say the north pole, and integrate over all rotations. This is a consequence of rotational invariance. Okay? Now you might ask yourself, why is he doing that? This is an integral over all possible unitary transformations. And what this means is this object must commute with every unitary matrix. I don't do the details, but if I multiply a unitary from the right here, I could put it in here. I could then, to a change of variables, replace u by something else that is rotated by v, and then it pops out here. Okay? Why is this interesting? Because this object is a matrix that has to commute with every possible unitary matrix. What does this matrix have to be? Which matrix commutes with every possible unitary matrix? Yes. And the identity is the only matrix with this property because we use all, it has to hold for all possible unitary matrices. So this tells us that A has to be proportional to the identity matrix. Okay? I'm sorry, I misunderstood you. I thought this is what you mean by symmetry, because it's also a symmetry argument over the sphere. I think it's kind of like using the intuition you use in a more algebraic framework.
That's the smart version of what I was
Okay? And now I can just insert it here. Sorry, now I apologize for, no, let me do this. I apologize for not having enough blackboard space, but I will make it worse. This tells us that the expectation value over h of v h squared is the same as v star, a constant times the identity matrix times v. This is what we just learned. This is a constant times v star v. This is a unit vector, so this is the constant. And the only thing that remains is to compute this constant. But remember that we started integrating over rank 1 matrices with unit length. So the trace of this object has to be 1. The trace of the identity matrix is not 1. So kind of like the trace of A is equal to 1 tells you that the constant has to be 1 over d. And so we really get 1 over d here, we get 1 over d here, we get 1 over d here. And this is exactly what you would get if you would do Gaussian integration and keep careful track of the length scale. It's just a bit more direct here, I would say. Okay? Yes? Remember that I sampled these vectors uniformly from the sphere. So they are unit vectors. And so here I went to the outer product of a unit vector with itself. If I take the trace, it's a contraction, and it gives me the inner product between the two vectors, which is 1. So what I'm doing here is I'm averaging a bunch of trace 1 matrices, and the average also has to have trace 1. Excellent question. Thank you for giving me the chance to clarify. Yes?
You didn't really use that they're complex vectors, right?
Kind of did here. Not yet. I will, in the second part, I will use that. But here, you can also use that for real valued vectors. And it's again very similar to Gaussian integration. Okay? So we've proven this. And what this geometrically means is that if I sample a very high-dimensional unit vector uniformly at random, it's in expectation almost orthogonal to any fixed reference I have. Okay? But this is now a typical argument. In the second part of the proof, we will use a concentration statement to show that not only is this true in expectation, but it's true with very high probability for any concrete instance. This is what's called concentration of measure. Somehow I can't let one up and the other one down at the same time. So it's sequential runtime with these blackboards. Part 2.
You use the complex already with this A, B, D, A.
Yes,
The complex numbers.
that's true. That's true. I'm not sure if you can make a similar argument with real numbers and the orthogonal group. If you say no, I believe you.
You need a matrix to have an eigenvalue.
Yes. Good. Thanks. I only ever work with with the complex case, and I know it's simpler, but I don't know how kind of like when the real case breaks down. Concentration around expectation. Okay. So now we've shown that for any fixed reference state, a random vector is very far away in expectation. Now we do a concentration argument around this expected behavior, which allows us to say that with very high probability, a randomly selected vector is far away. It's not only a typical argument, but like almost every vector I can sample has this property. And this is called concentration of measure in the context of spheres. And there's a beautiful theorem known as Levy's lemma, which tells you that. I think I write it more concretely and completely correctly in the lecture notes. Again, if I sample a vector uniformly from a d minus 1 dimensional sphere, complex or real doesn't matter so much, the statement I'm writing is for complex, and I have a function of h minus its expected behavior of h being greater or equal to epsilon is smaller or equal to 2 times e to the minus, I think, d times epsilon squared over the Lipschitz constant of the function, and then I think there's a pi cubed. Okay, it's a very general statement. It's a beautiful result. You can use it, prove it, using isoperimetric properties of the sphere in high dimensions. But what this basically means is as soon as your function is Lipschitz continuous, a concrete realization of your function where you plug in a randomly selected vector from the sphere is very close to its expected behavior, and the tail bound here is exponential in the dimension. Okay, so kind of like the probability of being far away is exponentially suppressed. It's a very powerful result. It's more powerful than the one we need. And because what we need is inner product with a fixed state of this guy squared minus the expected behavior squared, a concentration inequality for this. And I guess what you get here for the Lipschitz constant is then just a 9. Okay? But what does this say? We just computed that the expected behavior of the angle is very small. And so what this tells you is if I sample a concrete vector from this high-dimensional sphere, then the probability of it being not extremely far away is exponentially suppressed in the dimension. This is what concentration of measure means. I will now prove a poor man's version of this, which is good enough for our purposes, and I can prove it directly to give you the proof strategy. Levy's lemma is not so easy to prove. I will do a poor man's version. I claim that if I sample uniformly from the sphere, then the probability of the inner product squared between a fixed reference vector and my random vector being larger or equal to 1 minus delta squared. So remember, kind of like 1 is they are the same. 1 minus delta squared means they are pretty close. Is smaller or equal than 2 to the e minus d 1 minus delta squared halves. So in a way, this is a much, much weaker statement, because here Levy's lemma tells you that it concentrates very strongly around 1 over the dimension. Here I'm just saying the probability of being very large for this overlap or angle is very, very small. But this will be good enough for our purposes. Okay? How do you prove that? Well, the proof is we already know that the expectation value of this guy is 1 over d. This is what we just computed. Okay? And now, this is a random variable. I can call it sh. It's the inner product of v and h squared, and this is between 0 and 1. Okay? And what this tells me is that the first moment of this random variable is 1 over the dimension. Maybe I can compute higher moments of this as well, with similar ideas. I can now try to compute the kth moment of this guy. Okay? The way I want to prove this is to understand all possible moments. And if I've understood all possible moments, I can combine them to a concentration inequality. And we already started because we know the first moment. So what does the kth moment look like? It's equal to expectation value of h, v, h to the power of 2k. There's a kth power now. Okay? I now do exactly the same trick I did before, but with higher powers. I can rewrite this as, and now it gets a bit funky. As a product of 2k of these terms. So it's kind of like a homogeneous polynomial with the expectation value. And then, now I have to be a bit quick, but there's a 1-to-1 correspondence between homogeneous polynomials of degree k and Kronecker products of kth order. So I can also rewrite this as the kth Kronecker product of this vector, then pull in, this is multilinear algebra, the expectation into h star Kronecker k v Kronecker k. A quadratic function becomes linear in the Kronecker product of x with x. This is what multilinear algebra says. Okay, kind of like I have a polynomial, I have a homogeneous polynomial of degree 2k, and this becomes a kind of like a linear function on the k-fold Kronecker product. Okay? This was now a bit quick, but this is a generalization of the proof strategy I mentioned before. And this intuition with symmetries and unitary transformation extends to k-fold Kronecker products. And I wrote it down here. It's called high integration, and it's a very powerful tool in quantum computing. If you're interested in it, I recommend my Caltech lecture notes where I actually derived that. But it's a generalization of this argument we did here with the symmetries with respect to unitary operations. Because these are still random vectors from the unit sphere, and so I kind of can write them as a k-fold Kronecker product, and that means that this is still kind of like a big Kronecker product that is invariant under Kronecker products of unitary matrices. Joint basis transforms, if you will. And then you can use Schur-Weil duality for the representation theory of the unitary group to decompose this. And what you will see is that the uniform average over all possible k-fold tensor products of outer products of random spherical vectors gives you a projector onto the symmetric subspace of the Kronecker product. Okay, I know this is quick, it's written in the lecture notes, but this is just one way of generalizing this intuition that I showed you to higher powers. And if I plug this in here, I get V star Kronecker k, a dimensional factor, d plus k minus 1 over k minus 1. This is the generalization of the 1 over the dimension we had before because of the trace constraint. And instead of the identity matrix, we get a projector onto the totally symmetric subspace of k Kronecker products of this complex space. And this has something to do with the fact that homogeneous polynomials are in one-to-one correspondence with symmetric multilinear functions. And if we kind of like average over all possible multilinear functions, and we average a homogeneous polynomial, we better get kind of like the projector onto the space of all homogeneous polynomials, because we uniformly average over everything. Okay? Is a bit technical, but the thing is, this is the projector under the total symmetric subspace, and this is a k-fold Kronecker product of a vector with itself. This is symmetric. So this simplifies a lot, and you actually get d plus k minus 1 over k minus 1, a combinatorial coefficient, and this is smaller or equal than k factorial over d to the k. Okay? I could have achieved the same result with Gaussian concentration, with Gaussian integration, where if I go to higher polynomials, I go to higher moments of standard Gaussian vectors, and I will get these combinatorial factors. Okay? Yes. Yes. So what I just showed you is that the moments, the kth moments of our random variable are always smaller or equal than k over d to the k. And for those of you who might know a bit about concentration formulas and kind of like sub-Gaussian and sub-exponential random variables, this indicates a sub-exponential moment growth. Or more practically speaking, we now have control of all of the moments. I'm aware that this was quick now. I just wanted to show you there's a machinery that actually allows you to compute these things very efficiently. And now we have all the moments. And if you have all the moments, you get concentration. So now I'm ready, and I think I can do the concentration formula in one line. I want to compute that the probability of sampling a random h, vh squared greater or equal than 1 minus delta squared. I want to bound this from above. Okay? Now I rewrite this. This is the same as probability of h d times vh squared greater or equal than d 1 minus delta squared. And the dimension, I'm cocky because I know that all the moments have a 1 over d scaling, so I might afford an additional dimension here. I just multiplied both sides with a non-negative number. Now I can still modify this with a poor man's version of what's called the Laplace transform method, greater or equal than e to d1 minus delta squared. And I can do that because the exponential function is monotonous. Okay? So nothing happened so far. Now an inequality is, and as Amir says, at inequalities interesting things happen. I use the simplest inequality I know, use Markov's inequality. The probability of a non-negative random variable being large is smaller or equal than its expectation value. And this exponential assures me that both sides are non-negative. So what I get is the e minus d 1 minus delta squared. Right? And I get the expectation value of e to the d v h if I apply Markov. Right? This is good. This is very good. This is exponential concentration. This is scary. We somehow have to control this. And I write down a Taylor series. I'm allowed to do that because it's a convergent series. And then I have 1 over k factorial expectation of v h to the 2k. And here I have d to the k. Taylor series. Yes? Ah, thank you. Yes, I will need that. Thank you very much. This is duly appreciated because I think I will need it now. Yes, I need this to overcome. Thanks. Okay. And now we plug in the moments we've seen. And you can see something nice happening already. Kind of like, let's do it here. This is smaller or equal than e to the minus d 1 minus delta squared over 2. And now here in the sum, here another inequality, I plug in this crude moment bound. And what I get is a d to the k over k factorial times a k factorial over d to the k 2 to the k. A lot cancels. And what I'm left with is this 1 over 2 to the k, so thanks for helping me out. Because now this is a geometric series, and it's 2. And this is what I claimed. Exponential concentration that tells us that a randomly selected vector is with extremely high probability very far away from any fixed reference. Okay, and I wanted to do this argument, which is a worse argument than Levy's lemma, but I think it tells you where this comes from. Kind of like how you can derive these techniques by yourself, and we will need that for the partial de-randomization in the afternoon as well. Very good. Thanks for staying with me. Now, in the last 5 minutes, we have to put everything together, and we can do that. Okay, thanks. Yes?
Can you just explain again the link between Levy's result and the one we proved?
Kind of like what I proved is kind of like we have kind of like a very easy function, a quadratic function, which is a kind of like a distance measure. Where like 1 is kind of like they're very close, and 0 is they're very far away. And in the first part of the proof, we just looked at what does a typical vector behave. And we saw that a typical vector is very far away from any fixed reference vector. Now what Levy's lemma in concentration of measure would tell you is you would bound a deviation, an actual deviation of a concrete realization from this expected behavior. So the probability of deviating by more than epsilon from the expectation value, which is small, which is a strong statement because it basically tells you that everything concentrates around the equator of a high-dimensional sphere, if you think about it geometrically.
In terms of the mathematical formulation,
Yes?
here I can see every 1 over t, like the what's the link between delta epsilon and
what Levi's lemma tells you, the probability of being further away of this function from 1 over d than epsilon is exponentially small. And now it's set 1 over d to 0. So this kind of like tells you the probability of being even larger than epsilon for this measure is exponentially small. And what we now proved is the probability of being at least 1 minus delta squared, so on the other end of the spectrum, is exponentially small. This would be good enough for our purposes, but it's a much weaker statement. Levi's lemma tells you the probability of being larger than epsilon for this guy is already exponentially small. And we just proved the probability of being larger than 1 minus delta squared is exponentially small. But the advantage is that this is kind of like a general technique that you can really prove based on moments, and Levi's lemma you can't. You could put epsilon here as well. I just chose 1 minus delta squared because then this is kind of like, if delta is a small number, then 1 minus delta squared is almost 1, and so it doesn't affect it so much. Okay? We will kind of like, I will need this formula in the afternoon because we will de-randomize it. And this you can de-randomize, and Levi's lemma you can't. Thank you for asking. This was good for clarification. Now let's put everything together. How it started. A generic state vector is exponentially complex. Right? This is how it started. This is what I promised you when we started this lecture. How it's going. I just showed you that the probability of a randomly drawn vector to be kind of like reasonably close to a fixed reference letter vector is smaller or equal than 2 to the e minus d 1 minus delta squared halves for any v. Okay, for any reference vector. And this is exponential concentration. And remember that in quantum computing, d is 2 to the n. So this looks very similar to the 2 to the 2 to the n, the doubly exponential growth that the gentleman in the center used for Shannon's counting argument. So kind of like here we have it double exponential. We don't have it in counting, but we have it in probabilistic suppression. Okay? And now all we need is part 3, which is a union bound. This statement is true for any v. Now I can take a collection of v's and ask about the maximum, the closest of these v's. What is the probability, if I randomly sample a vector, that the maximum over v in an entire set greater or equal than 1 minus delta squared? So now not a single vector, but many vectors. Then the union bound or Boole's inequality allows us to kind of like pull this maximum out and bound this by the sum over the probabilities. Right? And now I can use my doubly exponential concentration to see that this is equal to the size of the set of vectors that I do times e to the minus d 1 minus delta squared halves. Okay? How large does this set have to become until this is not doubly exponentially small? It has to become doubly exponentially large, right? So kind of like this is tiny until VR is itself of order e to the d. I'm simplifying a bit. I do it more carefully in the lecture notes. Okay? And now we're there, and we can use the second part of your argument. Right? In the classical proof of Shannon's complexity for circuits, the first argument is that there's 2 to the 2 to the n different functions. And the second part is, let's just count circuits. And if I have a circuit of size r, the number of circuits I can generate is at most exponential in r, right? And so in order to get doubly exponential size of different candidate circuits, I need an exponential scaling in the dimension. Okay? So the last part is, let VR be the set of all state vectors generated by quantum circuits of size r. Okay? Then we can count them. Then we can count, like in the classical case, how many different circuits can I build, which is an upper bound to how many different state vectors I can reach. And now if you remember yesterday, a quantum circuit contains gates from an elementary gate set, which consists of 3 gates. Hadamard, T-gate, which are single qubit gates, and C0 gates between pairs of qubits. Now if I invest a single one of these gates, how many different choices do I have for the first gate? It's surely smaller than 4 times n squared. Why n squared? It's like an upper bound, but the C0 can connect any pair of qubits. So there's n times n minus 1/2 many possibilities. I count this with n squared. Then we have 3 elementary gates. And I also include the identity gate, because this allows me also to compute all circuits which are smaller than r. Because if I choose to put an identity gate there, I get a shorter circuit. So this allows me to count all circuits of size up to r. And then I do this r times. And let me just rewrite this as 2n to 2r, to the power of 2r. So, and with this, we are almost done. Because then we have that VR times e to the minus d1 minus delta squared halves is the same, is smaller or equal than another inequality where we do now circuit counting, 2n over 2r times e minus d1 minus delta squared halves. And this is tiny until in the lecture notes I write it more precisely, but we will see that r has to scale linearly in d, which is exponentially in the number of qubits. So kind of like until r is approximately d over log n. This log n comes from the fact that we have an n here. And this d is 2 to the n. And this finishes our counting argument. So when I choose a random state vector uniformly from the sphere, then the probability of it being complex in the sense that you cannot approximate it with circuits of size r or less is exponentially kind of like close to 1. The probability that it can do that is exponentially, kind of like doubly exponentially small until your circuits are exponentially deep. And then this probability becomes kind of like large, and then you cannot exclude the possibility of having a circuit approximation. Okay? And the last thing I want to say is here we used the uniform measure over the complex unit sphere, which is a fair measure, which also, like in the Shannon case, allows us to convert this probabilistic statement into a quantitative statement by using Laplace's definition of a probability. The probability that something happens is equal to the good case, number of good cases, over all cases. And so with this reasoning, we can also use this probabilistic assertion to say that almost all n-qubit quantum states are exponentially complex in the sense that it is impossible to generate them with quantum circuits that have a size that is smaller than exponential in the number of qubits. And this is basically exactly what Shannon said, but in the quantum case. Thanks for sticking with me. I understand that this was much more technical than the last lecture, but I really believe that this is a versatile proof technique. And today in the afternoon, we will actually de-randomize this to make statements about complexity growth in growing circuits. So I really think that this is a useful proof technique that can be applied to many other problems. Thank you.